Good afternoon, all. We start the 11th lecture in the series of statistics in research methodology. Let us quickly summarize what we have discussed till date. Initially, we started with the introduction of the subject statistics for daily life as well as research. Then the measurement of physical quantities and the parameters affecting the measurements, the results of measurements, appropriate way of presentation of data, as well as the associated accuracy, precision, ways to improve all these things, significant figures, place value of digits, rounding of error propagation, and the rules to each one of these. Then various types of measurements, namely gross, systematic, and random errors. In order to understand the characteristics of repeated measurements or random errors, we have understood the properties of Gaussian distribution function, mathematical expression, and the associated statistics, namely mean and standard deviation and variance. Then the confidence level, confidence interval, and confidence limits. Then the discrete and continuous probability distribution functions. All these distribution functions which we had discussed today are more or less symmetric distributions. Today we will see some asymmetry in the distribution. Then the hypothesis testing, we had learned Z and P statistics initially. The errors during hypothesis testing, namely type 1 and type 2 errors, also known as alpha and beta errors. The flow diagram to conduct the hypothesis testing, that was also elaborated, and in each of the examples we had followed the stepwise procedure to derive the conclusion from the hypothesis testing via null and alternative hypothesis. Then we had learned the minimum number of replicate measurements in order to get quality reliable data from the experiments which we propose to do. So initially itself, we get an approximate idea. We had seen from the T statistic that around 6 number of replicate measurements are more or less sufficient in the general cases, and the number of replicates depend on the level of measurand also. That also we had seen later on. From that, we had went ahead with reliability interval, the other statistics, namely chi-square and F-test, where variances are, ratios of variances are compared. The further extension of the F-test is the analysis of variance, namely short formed as ANOVA. Then the correlation between two variables, dependent and independent variables, which is explicited as product moment correlation coefficient. Further, if there is a linear relationship, how to derive the relation between these two variables, dependent and independent variable, via method of least square fitting. There we had seen both ordinary and weighted least square fitting, and the utility of both of these fittings as per the situation, as per the necessity, as per the requirement that we had discussed in the previous class. And towards the end of that lecture, we had started the discussion regarding if at all there is a variation assessed via the F-test. That means alternative hypothesis is holding during the F-test. That is, there is significant difference between the data being compared via F-test. How to ascertain which of the set of pairs of data are contributing to the significant difference, that is done via the least significant difference method. It is generally used to understand if at all there is a difference in the ANOVA or F-test, that is variance ratio test, what could be the cause, whether we can address that root cause and try to overcome that cause. That is done via the least significant difference method. Alternate problems are like if there is one mean which is substantially different from others. If at all it is a gross error, we could get rid of it via the outlier test. But now, even after rejecting the outlier, we find that the data sets are of two different populations. They are of two different populations, or these means are different, entirely different. That is not caused by statistical variation, since there may be a systematic error. So, or if they are of two different distinct groups in the populations. These all can be addressed via the least significant difference method. How do we do that? The steps are given in the box down. In this method, the input data sets are arranged either in the ascending order or descending order. Then what we do is we take that we make them into different pairs. All the possible pairs are made. The difference between two data points made as pairs are then calculated. Then this difference between pairs of data, several such pairs are made. The difference between this pair of data and the least significant difference, which is calculated via the equation shown over here, wherein the t-value and the mean square of the errors are involved, and the number of data points, individual data points in the individual contributors. We will see one example also how it is done. Then once you see that if the difference between two pairs of such data which we had taken, all such data, if this difference is larger than LSD, then we say that yes, there is a significant difference. The data may be of two different populations. The means may be different. The conclusions are derived thereof. For example, you will get a feel of this least significant difference from this example. Earlier, we had done for ANOVA evaluation also the same question, wherein we found that 5 analysts had done the determination of calcium via some analytical method. And each of the analysts has done 3 replicate measurements. We had calculated the variance ratio, and we had compared the calculated F value to the critical value. All this data we had discussed in the last but one class. From that discussion, we concluded that since the F calculated was greater than the critical value, we had come to the conclusion that there is significant difference among the analysts. Then from that point, we start now today. If there is a significant difference, what could be the cause? Which analyst is showing the different behavior compared to the others? For that, we make pairs, say analyst 1 and 2, analyst 2 and 3, 3 and 4, like that. All possible pairs of combination of these factor values, individual contributors are made. Then we find out the difference, calculate the LSD, least significant difference, compare the data points. Here in this set of data, if you do the calculation via applying the t-value of 2.234, 95% confidence level at 10 degrees of freedom, this data is taken from the critical values of t for two-tailed t-test. And apply the equation over here. The MSE, this value comes from here. Okay. MSE comes from here. And each analyst is doing 3 replicate measurements. So the value 3 comes from here. T value comes from the critical table. Digit 2 is there in the equation already. So you get the LSD as 1.16, and generally the trend is the steps proceed like this. We do from lowest, then next, like that, ascending order. One can do descending order also, doesn't matter much. Just identification should be properly given. Then you take the difference between each of the pair. When you see that the differences are higher than this LSD value, that is 1.16, then we say that there is significant difference. Whereas in the last one, 4th largest and the smallest, that means 9 and 8.7, analyst 4 and analyst 2, there is no significant difference. If we start making pairs of these individual contributors, you will see that the total number of such pairs one can make is IC2, I combination 2. That 2 comes from two data each we are making pair, and I is the number of factors involved in the entire measurement process. Here the number of factors are 1, 2, 3, 4, 5. So 5 C2 will be 10. 10 such combinations can be made. And the conclusions, all the conclusions are given here. Analysts 3 differ from 4, 5 differ from 4, 1 also differ from 4. So all the analysts 3, 5 and 1 differ from 4. But analysts 2 and analysts, they have similar properties, similar results. There is no significant difference between analyst 2 and 4. Similarly, you do the difference calculation comparison with LSD. you can come to the rest of the conclusions, namely analyst 3, 5 and 1 differ from the second analyst. Analyst 3 and 5 differ from analyst 1, and analyst 3 does not differ from analyst 1. So you can say that the last two sets, analyst 3 and 5, analyst 2 and 4, they are representing similar population, whereas the other pairs show, if you take them separately, individually, you will see that, yes, these have significant difference. So in addition to F test, wherever required, one has to conduct T test to derive the relationship between populations, sample populations. So you see, not only F test will give you the ultimate conclusion, sometimes you may have to use combination of statistics to derive conclusions. As I told you in the initial slide, till now, whatever we had studied was the presumption that all the statistical distributions which we studied, Gaussian, rectangular, triangular, or binomial Poisson, Bernoulli, all these distributions, we presumed that they are symmetrical. They have some center point and symmetry on either side, left or right, or lower or top or bottom. But sometimes in real situations, you see that the distribution is not symmetrical when we come to the real life scenario. There may be asymmetries. Maybe the population will have a longer tail on the right side, upper side, or sometimes longer tail on the lower side. Sometimes the peak position may be not sharp. You may have multiple peaks also possible. Real population will have different characteristics. In those cases, you may have to apply parameter-free statistics. Non-parametric statistics should be applied to get the corresponding values. Here, 3 figures are given. In the first figure, you see a large tail on the right side. Right side, there is a huge tail. That is easily visible by the shifting of the position of the mean towards the right side compared to the mode. Mode is the value which has got the highest frequency. Median is the midpoint when you arrange the data in one particular, say, ascending order, the data at the mid position. So median also gets shifted and mean also gets shifted from the mode towards the side where the tailing occurs. And in the second figure, you see the tail portion is on the lower side or the left side. Then you see the mean is getting shifted towards that side. Median also getting shifted from the mode to the same direction. So the shifting of the mean or median will show you from the mode position will show you there is some skewness. Skewness is defined as right skew or left skew. Other names are positive and negative skews, similar, respectively. And in Gaussian distribution function, we had taken the property, we had presumed that it is symmetrical with 50% of the total area covered by the right portion, another 50% on the left portion. It is symmetric with respect to the center one. But in reality, it is not the case. We may have skewness, left or right skew, depending on the nature of the population. That time, mean will not be the ideal statistic to compare. Then mostly we go for mode for a comparison of data. To have a reference point, you see the mode remains the same, whatever be the peak post. Sometimes what happens, the data will have multiple modes also. Then you cannot apply simple calculation. If at all there is a single mode, you can calculate one Pearson coefficients in order to assess whether there is skewness or not. If you do the calculation of Pearson's coefficient as shown in the left side of the screen, you can see for those particular data having singular mode, the left one equation is used. If you have multiple mode or flat region of population, flat distribution of population, then we go for the Pearson's second coefficient, which depends on median, not on mode. Then once you calculate this coefficient, you can get idea regarding the skewness of the distribution. If this coefficient value comes out to be between minus 0.5 to plus 0.5, then the data we presume that it is symmetrical, more or less symmetrical. If the calculated coefficient is having a range of values between minus 0.5 to minus 1, as well as plus either of this side, plus 0.5 to plus 1, either of these, within this range your value calculated value comes out, then we say that it is slightly skewed. It is not much visible, but there is some skewness in the data. You cannot really apply the mean and standard deviation. If the calculated value of Pearson's coefficient comes out to be larger than minus 1 or plus 1, larger than 1, magnitude being larger than 1, then we say that it is heavily skewed, then parametric statistics should not be applied. Similarly, another property of distribution, real life situation distributions are heavy tailing on either side. Maybe the distribution may be symmetric or asymmetric, but tailing is heavy on particular side. So if you see in this figure, the green curve represents the ideal situation or Gaussian distribution. There is no tailing. This tailing is called kurtosis. Kurtosis, if it is 0, you will see an ideal situation. But if the tailing is less and you get plateau regions on the midpoint or the mode region, middle point, mean region, then we say that there is an excess kurtosis. The curve is skewed towards the center point and the mode becomes flat. The mode position becomes flatter. Tailing portions are removed. The total area under the curve remaining almost the same. So this is called a plateau kurtosis. The skewness becomes positive, negative, small this thing, variation is there. The tailing is reduced. Tailing is reduced, negative tailing, that is plateau kurtosis. If at all there is an excess of tailing as shown by the blue curve in this figure, you see that a sharp midpoint is there. However, the data has got excess of tailing, which will lead to if you do the hypothesis testing by comparison of two distribution of data, you will see that the type 1 error, type 1 and type 2 error may be higher in such cases. Ideal situation will be the green line. And in real life situation, if you have larger population towards the midpoint, you will have a plateau. You have more number of population on the midpoint, you will have a plateau. That's called plateau kurtic distribution. But if you see that the data points are scattered apart from the center point, the probabilities are not decreasing drastically when you move away from the center, then you will see that there is an excess of kurtosis, excess of tailing. So it is called a leptokurtosis. Kurtosis can be calculated and assessed. Then once you see that kurtosis is large, then you go for non-parametric distribution. Now we come to another term called power of a hypothesis test. We had learned the types 1 and 2 errors during hypothesis test. Type 1 error is also known as alpha error. Type 2 error is known as beta error. The power of a hypothesis test is nothing but the probability or the area shown by this gray shaded region. Gray shaded region is called the power. That is defined as the power of a hypothesis testing. It is nothing but the ability of a in hypothesis testing, what we do, initially we propose a null hypothesis saying that two distributions, for example, here two distributions, one shown in blue line and both are blue line, but one on the left side, another on the right side. If initially we presume that they are identical, if they are identical, what happens? There will be overlap of the two distributions. That is the most ideal situation. They overlap. Null hypothesis is perfectly acceptable. But in real situations, it doesn't occur most of the time. There is probability that the distributions are separated out. Okay. If the distributions are separated out and the null hypothesis, we start with the first one. This is the first curve, this is the second curve. Then you see that wherever the tail portion or the rejection portion of the first curve via any significance test, that will correspond to the alpha error. For the second curve, wherever is the tail portion, that will correspond to the beta error. And the null hypothesis, power of a hypothesis will be defined by the area. The larger the area defined by 1 minus beta, better will be the power of the hypothesis test. Actually, these hypothesis test powers are used in order to come to a conclusion. If at all we are in a doubt whether which statistic to be applied in a particular situation, whether I should apply T statistic or Z statistic in a situation. For example, if we have say around 25 to 30 data points are there, which one will be more suitable? That will be decided by this power factor. That is 1 minus beta. We can calculate this alpha and beta type of error. Normally, we keep 5% significance, which will correspond to 95% confidence, and 0.05 in terms of fractional significance for alpha. Beta, till now, we have not given any generalized proposition for beta. That we'll see after discussing this power of the hypothesis, which is generally taken for the beta value. Okay, if the beta values are plotted against the mean value and the difference between the true value, these curves are called operating characteristic of the test. So these are the terminologies used to evaluate whether my statistic is proper or not. If we plot the beta values against the alternate possible values, difference between the mean and the true value, then this resulting curve, if we plot beta, then it is called operating characteristics. If we plot 1 minus beta versus the difference between measured value and true value, then it is called power of a hypothesis test. So we will see the power curve more in detail in this class. The power curve plots the power of a test versus the difference between the mean and the targeted value. Here, power is 1 minus beta. So in power curve, you can take specific number of data points or the number of measurements, significance level alpha also one can define. So in the curve given in the left side of the screen is a typical example of a power curve for a sample size of 32 at significance level of 5% or 0.05 fractional significance level. Okay. In this curve, you can see that it is a downward Gaussian. You can say it is a downward Gaussian, symmetrical with respect to the central point. If the difference is difference between the measured and the true value is 0, that means the power will be equal to alpha. That is point that will correspond to around 0.05 in the power curve. So whatever be the value of alpha, that will be the minimum in the power curve when the difference between the true and measured values is 0. When the difference is 0, the minimum of the power curve we attain, that will be corresponding to the value of alpha. Generally, if you see, if there is a dot shown over here, generally the larger, the closer the value of power to 1, power is calculated as 1 minus beta, as I told you. The smaller the value of beta, better will be the power. The larger the power, the closer the power to 1, the better the power of the hypothesis test is better. That means it is more suited for particular analysis, particular application. The idea is to go to those points which are near to or closer to the higher side, upper side. As we come down, the power of the hypothesis test decrease. For example, if I compare two tests, one of them is giving me power around 0.9, another one is giving me power around point. Actually, we compare the powers at a particular distance of two curves. I will show you in the next slide. That will be more visible. As the difference approaches zero, as I told you, the power of the curve decreases. If you move away, if the populations being compared are moving away, that means the difference is increasing. The power, the ability to differentiate between these two means increases. That is like a simple visual representation itself. If you are able to keep the two students apart, then you can see that he is different, the other one is different. But if they are coming closer, it will be difficult for us to differentiate between their performances. As the power of the test increases and approaches unity as a true means gets further from the null hypothesis value. The power is defined like that only, the ability to reject the null hypothesis when it is true, when it is false. Sorry. So it is easier to deny the hypothesis as it gets further from the truth. If we want to differentiate between two values, the ability to differently see those values, that is the power of the hypothesis test, whether this particular statistic is able to differentiate between the two. And as we repeatedly saw, as a true value and the mean value coincide, the power of the hypothesis approaches alpha. So that will be the minimum power attainable by any such statistic. If you try to decrease the value of alpha at a particular sample size and level, you will see that the power curve will have lower value all the time. You may not be able to reach up to that higher value, near one. If you start from lower, I will show you in the next slide. So low statistical power is inferred when you have large risk of committing type 2 error, that is beta error, false negative error will be higher if the power of the hypothesis test is low. If the statistical test has got high power, then the risk of committing type 2 error also decreases because it is defined as 1 minus beta only. So generally, we already till now we have seen that we keep alpha as 5%, and the general consensus is to go for around 80% statistical power for any hypothesis test to be qualified for the purpose. So in the previous curve, if you see the portion which is marked in the red, the oval shape, that portion is the ability of the curve where we keep it as the qualifier in the test. And as we have seen in the t-test and other statistics also, if you increase the sample size, you are able to improve the quality of the data. The power also increases similarly. The trough of the curve decreases and becomes sharper if you increase the number of data points. So these are the experimental evidence for increase in power as a function of sample size. Here in the right side, you see different curves wherefrom you can appreciate that as the curve becomes flatter and flatter, the power of the hypothesis decreases. The one which has got sharp rise from the 0 to the largest possible value, that is 1, near to 1, that one. That means when you go near to the blue lines, blue curves, you see that power rises rapidly. Power of the curve, ability to differentiate between two populations increase rapidly. The closer you approach the blue curve, the better is the power. And if you are comparing between two statistics, one is having a distribution like this red curve, another one is having a distribution like this blue curve, then the blue one will be selected over the red one. The comparison of the power of the hypothesis test will make you able to take a decision between two statistics, which one to take in a particular context. So if a hypothesis test has got low power, we may fail to detect the difference, which is practically significant. We may lose very important information. So high power is better whenever the null hypothesis is false. Whenever you want to establish the difference between two populations, you go for a high power test. Whenever you want to show the identity or integrity between two sets of population, power does not matter much. At a fixed significance level, the steeper the curve rises towards the one, the better. Otherwise, the shallower, the worse it is. It is visible from the curve shown over here. That is all about hypothesis testing. Now we come to design of experiments, the general introduction of design of experiments, and a few of the examples we will discuss in today's class. As we had already defined the term factor, any parameter, any contributor which will lead to variation in the result, that is called factor, contributor or factor or this thing, group, variance, like this, these terms are used. Variable, these terms are also used for defining the parameter or the input variable which is affecting the final outcome of the experiment. And the various levels of the various functions of the variable, the input variable, various levels in which it can affect, that is called the level of the input variable. And these factors, these input variables, sometimes they are under the control of the experimentalist. For example, the pH in which you are doing some experiment or the wavelength of a particular emission line or absorption line, you can choose for a particular analysis. For example, in the determination of calcium, we had chosen the particular wavelength for determination. But at the same time, if at all the laboratory environment is affecting a particular measurement, you will see that many a time this variable is not under the control of the experimentalist. For example, the temperature of the room is increasing on a hot summer day. It is not under your control. Then maybe you may have to do thermostat the experiment and try to overcome the effect of these uncontrolled factors. Sometimes the instrumental fluctuation which is not visible to the experimentalist, this also may lead to variation. If at all it is a large variation, definitely the outlier will give you, or the outlier test will help you out. Sometimes the fluctuations may not be much visible, but there is a uncontrolled variation in the outcome. So that is contributed by the random errors. That is what we had discussed all during these classes. And these factors, sometimes these factors may manifest as just as a qualitative influencer. Sometimes they give change which is quantifiable, measurable, quantifiable changes may be there. For example, the presence or absence of a catalyst may lead to change in the rate of a particular reaction. Or if the atmosphere is changed from air to vacuum to helium or some other atmosphere, you will see variation in the reaction kinetics, or maybe the variation in the formation of the particular product. So these are qualitative factors which will change the ultimate product, which you cannot numerically predict what will be the change or the outcome, magnitude of the outcome, you cannot predict. But there is definitely an impact of variation of these factors. Whereas some factors, you can say that yes, by changing the pH from 1 to 2 to 2 to 3, you expect a quantitative change in the output, which can be calculated and predicted. Then that becomes a quantitative factor. Or maybe if I do the same experiment at a higher temperature, I will get better yield. Maybe the yield will be increased by 50%. That way, the parameter which has got a magnitude and which will affect the result also in that proportion, it is called quantitative factors. So the factors may be controlled or uncontrolled, qualitative or quantitative. When we try to design, pre-plan an experiment, what we do is to identify what I'm supposed to do and identify factors which are going to affect the experiment, whether they are having, they hold much over the experiment than the experimentalist, whether I can control them, minimize them, or whether they are uncontrolled. Those things we can try to gather information from literature or previous experimentalists. You can get information from them. Otherwise, maybe some theoretical modeling you can do. And the idea of all the experimental design is to ensure the effects of uncontrolled factors to a minimum. So, though it is not ideally possible to get all the uncontrolled factors nullified, but you can minimize, you can get the effects minimized. And then you can have a statistical method for interpreting the results. We will see one example in this regard, how to interpret the data analysis using some statistical method. One such design of experiment we apply in chemistry is the chemometrics. That is the application of mathematical and statistical methods to design experiments, optimize the conditions of the experiment so that you get the output as desired by the analyst or experimenters. And whenever we need to analyze the data, whether we can gather the data together, analyze them in group, or whether you have to do separate analysis or gather them together and apply the specific statistic data so that you can save time and get useful information, gather information more logically from the data available to us. So this way statistics, as we discussed in the very first class, statistics is very largely used in chemometrics. So essentially chemometrics is the planning, optimization and analysis of research data. For this, the procedure should be like this. What results are required, what results we anticipate, and what are the factors which are going to affect the outcome of the experiment. And then accordingly, if at all there is a reference or a literature available, select an appropriate design to solve the problem. Otherwise, go for iteration, maybe combination of the available resources you may have to apply. Then do the real experimental work, then come back and compare it, separate the data based on their properties, maybe similarity, differences, or unexpected results. That way, categorize the data, make them into different groups, compare the data with the available literature, and then come to the conclusion. So the experimental design goes like this. The designs can be done either simultaneously or sequentially. I will tell you what is simultaneous design. In simultaneous design, either the experiments are completed, all the experiments are completed. This is regarding the analysis of data. Otherwise, one can do anticipate what are the factors going to affect my experiments, combine all the factors and do simultaneous variation of all these factors. For all these things, statistical softwares are nowadays being used. We will see in the next class what are the softwares available for doing such exercises. Otherwise, systematically, if you have enough time, you want to understand the impact of each of the factors separately, you plan the experiment stepwise, slowly. Study one factor, get to the conclusion, go take another factor, get to the conclusion. That way you can do. But it is a time-consuming, elaborate process. If you want to save time, energy, instrument, and whatever reagents you use, you go for simultaneous design of experiment as well as simultaneous analysis of data also. And the analysis part is divided as univariate, multivariate, univariate, bivariate, and multivariate. For example, if you have different variations as a result of changing factors, you can combine similar outcomes together, combine them together and study their properties, characteristics, and try to apply whether whatever distributions we have studied till date, any one of them is applicable, valid over your situation. You can go ahead with that. If you find any asymmetry or skewness or kurtosis in that one, come out of these parametric distributions and use non-parametric distributions. All these conclusions are derived from the analysis of data. If it is not singular data all the time, you may have to think laterally also. Not only your result, you may have to compare with the data available in the literature and try to identify the sources of variation, if at all there is any. If not, then you have to ascertain that yes, your method is working fine. That way you can come to the conclusion. We will see one specific case of factorial design of experiments here. Based on the number of factors and the number of contributors to an experiment, one can design an experiment and optimize the parameters, which are like parameters of the factor, as well as the final results one can analyze. We will see in the next slides how the analysis of this designed experiments will help us to come to meaningful conclusions. In a factorial design, if a factor is having different contributing levels, different sets of values which are affecting the result substantially, we call those as levels. And what we do is we do design the experiments by changing the factor values from one level to another level. The smaller or lower value we call as low level, and the other one as the upper level. Generally, we keep, for the simplicity, we keep two-level factorial design, but ideal situation will be multi-layer, a minimum three-layer factors. Lower one, middle one, and the upper one. So in this discussion, we keep two-level factorial design for us to make the situation simple as well as make it understandable. And the number of experiments to be conducted to understand the effect of these factors at various levels on the outcome is equal to the level to the power factor. The number will define as the level, and the integer value will be the level, and the power will be the factors, number of factors. For example, if I have got 3 factors and 2 levels, the total number of experiments to be carried out, we call it as treatment combinations. It will be level to the power factor, that is 2 to the power 3. Okay, that way. If at all there are 2 factors and 3 levels, the number of treatment combinations will be 3 to the power 2. And if at all we are doing each of these treatment combinations repeatedly, the number of repeated measurements times this value, that will be the total number of experiments to be carried out. So if we are doing R repeated measurements, R replicate measurements, R into m to the power n, where R represents number of replicate measurements, m is the number of levels, n is the number of factors. That many number of experiments one has to do practically in order to analyze the data meaningfully. And if at all 2 factors are having some correlation, they are interacting with each other and affecting the final outcome in different way, then we say that there is an interaction between the factors that will be clear once we discuss a real worked out example. In this example, we see the utility of this factorial design in order to derive conclusion during the study of impact of various measurement parameters. One particular case is the measurement of absorbance of a calcium solution. This calcium solution examples we had done for the ANOVA also. Say, for example, if one person is doing the determination of calcium using atomic absorption spectrometry, the factors which may affect the measurement are the flame height, lamp current, and fuel ratio, fuel to oxidant ratio. These factors are given identification as A, B, and C. So we see the impact of variation of A, B, C factors on the outcome will be the measured absorbance. Measured absorbance, what will be the outcome? And the factors which we are going to change is flame height, lamp current, and fuel ratio, named as A, B, C identification. And this, how these values are arrived, that I will tell you. One is a low, you can numerically see that this is a lower value, 15 is lower compared to 25, 2 is smaller compared to 3, 4 by 9 is small compared to 5. So smaller value take together and up higher value on the other side. Lower values normally we give as a symbol minus, high value plus. Since there are 3 factors and each factor is represented in 2 levels, you will see that 2 to the power 3, 8 treatment combinations are possible. If at all 2 replicates are done for each of these factor levels, you will see 2 into 2 to the power 3, that will be 16. 8 into 2, 16 such total experiments should be done in order to get the data, reliable data from this set of. The idea is to see whether flame height, lamp current, and fuel to oxidant ratio will have any impact in the measured absorbance of calcium during this particular exercise. So for example, as I told you, we are doing the change in the flame height from 15 millimeter to 25 millimeter. When we are changing one parameter, we keep the other. Ideally, in sequential design, what we do, one parameter, one factor changing at a time. But in simultaneous one, you do all the entire data set and try to come to the conclusion. Here you see the experiment goes like this. Here you can do the flame height at low, then fuel ratio at low, lamp current also at low value. All the values are low. So in bracket, one lowercase l is written. Flame height, fuel ratio, and lamp current, all the contributor factors. This is A, this is B, this is C. All A, B, C are low. Whenever a contributor or the factor is small, you write either the absent, there won't be any letter, or all the contributors are low, then you write lowercase l on the left side, in order to indicate that it is a lower value of all the factors. If at all one of the factors is having higher value, then keep the lowercase letter of that factor. For example, in this one, A is written, a letter A is written. That means here flame height is taken as at its higher value, 25. At 25 millimeter flame height, other factors, fuel ratio and lamp current are kept low. The absorbance measured, that is multiplied by 100 in order to show it in the table. That value is given. Here C indicates that the C factor, that is the fuel ratio, is high, other factors are low. When I say AC, it indicates that the flame height as well as fuel ratio, A and C, both are in their higher value. Both are in their higher value. We are seeing the change in the absorbance as a result of change in these input parameters, input factors. In the first case, all the values, flame height, lamp current, and fuel ratio are kept low, and the absorbance was found to measured absorbance was found to be 54, multiplied by factor 100. When we keep high flame current, we will see a different value. This is a resultant of 2 replicate measurement each. Each of these values are average of 2 replicate measurements. AC indicates that flame height as well as the fuel to oxidant ratio are high. That means at 25 millimeter flame height and fuel ratio 5/9. Fuel ratio 4/9 is the lower one, 5/9 is the higher one. So that way, this point all of you can read. It will be a high value of lamp current, keeping the low values of both flame height and fuel ratio. That way, this table you all should be able to read now. The left-hand side lowercase letters, they all represent, if at all a particular factor is kept at high level, these letters are written. If the letter is not written, that means the factor is at its low level. And the value, numerical values, are the absorbances measured during these experiments. Those are the average of 2 replicates each. And in order to understand the impact of these factors on the final outcome, initially we construct a table of signs where low values are given minus sign, high values are given plus sign. Okay, low values are given minus, high values are given plus sign. And if there is a combination of, say, flame height and lamp current, A and B, A is flame height, B is lamp current, C is fuel to oxidant ratio. If there is a combination, for example, in low, we have seen that both are low. That means both are negative. Then it will be a mathematical product of their signature. Minus into minus, it will be plus. And in this again, it is, you are keeping C value high, then it will be C value low, then it is singularly minus. When we take low values of either A and C, minus into minus becomes plus. So that way, this table of signs is constructed from giving low value a minus sign, high value a plus sign. And when you have combination of factors, it will be the numerical product of this signed combination. Okay, if you have a product AB, if both are having minus and minus into minus become plus. If you have a product or triple product of A, B, C, where A is having minus, A is having plus, B minus and C plus, then it will be plus into minus, it will be minus, minus into plus again, it will be a minus. So that it is simple mathematical product only. Signs minus into minus will be plus, plus into plus will be plus, plus into minus will be minus, plus minus into minus again it will be plus. And the rightmost columns, these are the average absorbances measured during the experiments. So that is where these numbers come from. And the lowercase letters indicate, as I told you, if it is A, that means the flame height is on the larger side, bigger side. And if it is B, that means lamp current is high. C indicates that yes, fuel oxidant ratio, it is high. If I say AB, that means flame height as well as lamp current, both are high. Definitely, if I say both are high, the third one is without, by default, it is in the lower value, minus value. So that way, this truth, some people say it as truth table. This truth table can be constructed, and the values, these are experimental values. How to calculate the effects? The idea of this exercise is to understand experimentally measured data are there with us, but in order to understand whether these factors have impact on the final result, if you are comparing individual data, you can do F-test, T-test, results, all the statistics which we had learned till date, all those can be utilized and come to the conclusion. But if you want to understand that there is inter-factor interaction, for that, this type of exercise will help you to come to the conclusion. For example, if a factor, say A, is interacting with the other one B and giving you a result which is unexpected and not anticipated from your experiment, that can be visibly seen from this factorial experimentation, factorial analysis of data compiled via the real experiment. For example, if from the table of signs, if you want to calculate what is the final effect of factor A, that is the flame height on the final absorbance values, you have seen wherever A is high, wherever A is high, that means you see the first column, wherever A value is high, means the A is plus, you take those values, sum it, since there are 4 values, divide by 4. Wherever A is high, A, B. Wherever A is high, I will just circle them in the first column. So you can see A, B, AC and ABC. Sum them and divide by 4 and subtract wherever A has got negative values, that is L, B, C and BC. You take the values of the response, or the absorbance is called the response. You will see the final effect of change in the flame height from low to high value, 15 mm to 25 mm will be final impact of minus 21.5 on the output or the response. That means as I increase the flame height from low to high value, the response is decreasing. There is an inverse relationship between the input factor and the response function. Similarly, if you want to calculate the impact of the lamp current on the response function, similarly, you can calculate the sum of those points where B is at high, then subtract the sum of those points where B is at low value, then you get divide by 4, then you get the value of impact of B, lamp current, on the absorbance of calcium solutions. Here again you see there is a negative sign for the number, indicating that if you change from low input to high input of lamp current, the absorbance value is decreased. Whereas in the case of the fuel ratio, you can see that the value is numerically positive, indicating that if you increase the fuel ratio from 4/9 to 5/9, the output or the response or the absorbance is increasing. From this page, this slide, we can conclude very well that flame height and lamp current has got a negative impact on the absorbance, whereas fuel ratio has got a positive impact just by seeing the sign of these values, impact values. And if at all B and C, the lamp current and the fuel ratio interact, they both have some common interaction point and give the outcome, then again you see that there is a negative impact, numerical value is small. So the impact, combined impact of B and C is that reduction in the absorption intensity, but the reduction is marginal. All these conclusions can be drawn from just by seeing this table of observations via constructing this truth table and calculation of the impact of individual as well as combined parameter outcome. So this way, from a single page of compilation of data, one can derive many useful information. If you do minimum set of experiments, later on you can plan accordingly. Future experiments can also be planned. You can see that this combination effect is magnitude is small, so that means their interaction, cross interactions are less. It will be much more visible in the coming slides also. Then, as I told you, we have to select the different levels of the parameter. For example, the flame height, we had 15 millimeter, 25 millimeter. What is the basis of selecting that levels of the parameter? That is shown over here. The levels should be such that the absorbance values which we measure or the whatever response we measure, that should be visible. There should be visible change in the response function. The levels should be selected in such a way that the response function changes are visible. And at the same time, if you can do more than 2 levels, that will be better. If you increase the level, accordingly, proportionately, the number of experiments will increase. The quality of data also rises substantially. This slide will give you the entire step of calculation to derive the final conclusion of which factor is affecting the final output. For example, we had combinations of flame height, lamp current, and the fuel ratio, and the observed absorbance values. Leftmost column should be readable to all of you, and the second one is the average absorbance values. The columns identified as 1, 2, and 3. I will explain how these columns values are derived and the final one. For example, for column 1, this method is called Yates method to derive the response function and calculate whether the value, the data obtained has got any significance, whether we can conclude from what we can conclude from this data. And finally, we see which factor is going to affect the final output. Nowadays, computer programs are available. You feed in the data on leftmost side only, the absorbance value and the parameters. The rest of the things are calculated via software. You get the ready-made output. But this will tell you how the calculation is done during the use of the software. What the software does is that the column 1 in this, here we have seen that 3 factors are there: flame height, lamp current, and the fuel to oxygen ratio. So 3 such columns are constructed, and in each of the column, this first number I will tell you how come the value 82 is derived. This is the sum of those values, first 2 set of values. All the parameters low level, then A at high, B at high, A and B both at high, C at high, A and C both at high, B and C both at high, all the factors at high. These are the input variations and the measured responses, average responses. Column 1, first numerical value is derived by taking the sum of the first two pairs. Second value is the sum of the second two pairs. Third value is the sum of these two. This value is the sum of the last set. So 4 such pairs are there. We take adjacent pairs and take their sum. Sum first, sum 1, sum 2, sum 3, sum 4. Then the remaining portion all are negative. Here what you do, subtract this 28 minus 54, that will be minus 26. 23, whatever we had summed, the reverse way you subtract. 28 minus 54, 23 minus 50, 52 minus 69, 47 minus 63. This is an example. Wherever you have your value, put that way. What you do is make them into pairs, adjacent pairs, sum them and fill the first 4 rows. In the remaining 4 rows, the pairs which we had done summation, take them in the reverse order and subtract. That way you construct the table, column 1 of this table. That is the third column identified as column 1. Then in the fourth column, similar exercise is carried out. Take the pairs, adjacent pairs, sum them, then get the 4 values, take the adjacent pairs, reverse them and take the difference. That way you are. Since there are 3 factors, do the exercise till this third level, then you will see that you get a total of 386, which will match exactly with the total sum over here. If you are getting this 38, these values identical, that means your exercise is proper. You can have a self cross check also. Similarly, you carry out the exercise again. Take the sum till fourth one, take the difference till the last 4. We will stop here just by concluding in this slide. Next class we will explain this again. But I told you just now, if you get both these values same, that means till now whatever calculations you have done is correct. Here, this slide we slope, just prior to that I will explain. Here you can see that the value 4a, because 4a value has been taken 4 times. In the previous one we had divided by 4 to get the value. You see there is a negative sign prior to that numerical value. Indicates that when you increase a, the output is going to decrease. When you increase b, the output is going to decrease. When you are seeing the combined effect of A and B, that is flame height and lamp current, you see that the impact is not much visible, almost near to 0. C, it has got a positive value. That means the fuel to oxidant ratio has positive impact. If you increase it, definitely the response is going to increase. The combined effect of A and C, flame height and fuel oxidant ratio, you see that it is going to increase. And combined effect of lamp current and fuel oxidant ratio, there is a small negative value. Value is negative. That means if you go to higher value, higher input parameters, you see a decrease in the response, but the change is not that much. For example, if you see 86 is the largest value, that means flame height has got the largest impact on the output, the response, the absorbance. Then you see 76, that means C, that is the fuel to oxidant ratio has got the next higher impact. That way, just by seeing the numerical values in column 3, you can conclude that this 386 has to cross verify. The numerical values, the larger the numerical value, higher will be the impact. The magnitude, the sign of that value will show you whether it has got positive impact, positive sign, negative impact, then there will be negative sign. So we stop here for the day. Any doubt is there, you can just write in the chat box. Otherwise, during checking, I will just summarize whatever we had discussed today. We had seen the least significant difference method to identify the sources of variation during the ANOVA testing. Then we had seen the power of a hypothesis test, then the asymmetries in distribution, experimental design, chemometrics, and factorial design, and the steps involved in the factorial design, and the conclusions we are making based on the design of experiment. From this point onwards, we will discuss in the next class. There are no doubt, we will stop at this point. There are no doubts visible in the chat box. Nobody has written. So factorial design, the inferences we conclude, we restart in the last slide, we start in the next class. Let us wind up then. Okay.